Okay, so the exercise. What I'm up to on my exercise. Final impulse response systems. And basically first question is about comparing the amplitude responses for different window shapes. Doing basically the same thing what I have done on my slides there. Then selecting a window and how wide window you need to take in order to change transistor bandwidth by the factor of your secret number. Yes. Really? That's bad. Oh, yeah, you're right. There you go. Now you have access. Ooh, see. Oh boy, that is very popular for a reason. Okay, good. But anyway, so playing with the system. So first one was the finding a window that fits into the stop band attenuation criteria. Then select one of the previous windows, how wide window you need to in order to change transition bandwidth by factor of 0.SSS. Okay. And then design a low pass filter with the following properties. Okay. What else? Then transforming again. Yeah. So basically, there's plenty of things to do here. I will start it now, but in 15 minutes I need to take a break. But you can basically continue working on the exercise, and then I'll come back and tell you more. So, finite impulse response system. Let me go and start my Octave graphical user interface there. There we go. So, how to design a low pass filter? FIR low pass filter. Okay. First, I need to start from somewhere. So let me first get some values here, like sample rate equals 2000 hertz. So this would be a system, data logger system or something like that. Sample rate. Okay. Then on this filter, what I would like to have next is, cutoff frequency. Let's make a low pass filter with the cutoff frequency with, say just for fun, 250 hertz. And now we just need to make the region of interest and make the sink. So my target here is now to find out a FIR filter of some length with, first, I can see that the cutoff frequency actually can be controlled. Then we go and smooth the window and do the rest of the magic. Okay, so my window sink would be simply, okay, I do one more thing. Fn equals Fs over 2. So that's just for fun, Nyquist frequency. There. So impulse response at this point would be just the box times SC divided by F. N times sink of N times TS meaning the end would be say -10 to +10, symmetric, times FC divided by Fn. Okay, that's the Windows sync. And then we just take a look at the frequency response. HH1. 1 is now the parameters for the feedback, and we have no feedback, only the first parameter, YFN. And then 1024 points and sample rate FS. I think it went something like this. And yes, wow. It's nice to show a demonstration that works. So basically, this is a low-pass filter by itself, which has 250 Hertz cutoff rate, somewhere in here, -3 dB points, about 250. And the stop band attenuation, actually the stop band starts around 300 Hertz, but it's only about 20 dB. Not too much. Okay. But we got the cutoff frequency fixed. Next step, the what is the stop band attenuation? With different window. Let's check what kind of windows we have. Do I have to load the okay, signal? Yeah. If you are using Octave, you may need to do this, but on Matlab you don't need to. Let's load control. There we go. Okay, so we have some signals, but I didn't see help window. Does it say? No, let's see. Does it say anywhere what kind of windows it has? Okay, now we can find some windows here. That was the Blackman, Matlab is here, and so let's see. I will take the help, for example, Blackman, and there's supposed to be also some hints for where to find. But anyways, you should, if you're using Octave, take a look at the what kind of window shapes there are on the Octave function reference list. Okay, for Matlab, I think you get help window. It gives you also the window types that can be used there. Okay, so I will start with the Blackman, and then basically let's make the window is Blackman, and basically it just needs the one single scalar as an argument, which tells you how many points, and this must be the same amount as you have the window width, meaning the length of my HH. And we transpose this one. For historic reasons, these window functions have always been single row vectors or single column vectors, but their system coefficients are row vectors. So basically we need to just make the dimensions to match. There we go. So remember transpose. Should I put it? Transpose needed. And let's take new figure and see what happened for the frequency response if we take 8H dot times WW. So this is the windowed sink. So that's what happens. Maybe I should actually zoom this a little bit. Zoom that one too, so to have them about on the same scale. Okay. So what happened to the stop band attenuation? Now we have about 70 decibels of stop band attenuation. Cutoff frequency still the same, 250 hertz here. The transition bandwidth got haywire. So now it's basically the transition bandwidth was about 50 hertz before. Now it has a transition bandwidth is about 300 hertz. But we know how to deal with that one. We fix these, fix the width. So if transition bandwidth is now 300 hertz, but should be, say, 100 hertz, then we need to have a wider wider window. Okay, and that will be, say, 3 times wider to cut it by the factor of 3. So basically we need to calculate the HH from not 10 to minus 10 to 10, but minus 30 to 30. Okay, we need to fix the window again, and then now we should have the that transition bandwidth again, where it should be. There we go. Yep. Oh boy, this is so sensitive today. Okay, so wider window, smaller transition bandwidth. And the ratio is directly how much less or more you would like to have on that transition bandwidth. Okay, that more or less covers the low-pass filter design part of the exercise. Now I need to go to another place for half an hour, about half an hour, I would say. So I will come there here at 4:30 or so and continue with this modulation to get the bandpass filter, high-pass filter, bandstop filter. 3:30, sorry. Yeah. Yeah, I'll be back in 3:30. No.